Today we are going to take up the third part of our chapter on alcohols, phenols and ethers. So, earlier we discussed about the alcohols and phenols, where we talked about their properties, their reactivities and their preparations, and today we are going to take up ethers, which are nothing but the dialkyl derivatives in a way of water. So, today's topic of discussion is ethers. So, the ethers are nothing but if you compare it to water. So, water is our H2O, and if you replace one of the hydrogens by an alkyl group, we say that it becomes an alcohol, and if you replace both the hydrogens by either the alkyl groups or one alkyl, one aryl or both the aryl groups, then in such case the resultant molecules are termed as ethers. So, these are the ethers which we are going to talk about today. So, if it is substitution by dialkyl, you call it as a dialkyl ether. For example, if R is equal to an ethyl group, you call it as ethyl ether or a diethyl ether. Okay. So, these are the molecules, a new class of functionalities in which your hydrogen of the water has been replaced by R. If you replace one of the hydrogens by aryl group, it becomes an alkyl aryl ether. Okay. So, this is an example of an alkyl aryl ether. So, you can have a phenyl ethyl ether or a phenyl methyl ether, which is called an anisole, and if you have both these functionalities as aryl groups, so it becomes a diaryl ether or a diphenyl ether if both aryls are phenyl groups. So, you call it as a phenyl ether. So, today we are going to understand some of the properties, reactions and preparation methods for these molecules which are called ethers. So, looking at the structure, you can find some similarities with water. So, the bond angle in case of water, if you see, the HOH bond angle for water is 104.5 degrees and it has a bent structure. Water is a bent molecule. You convert this to an alcohol, replace one of the hydrogens by R, and when this R is a methyl, example a methanol, then your bond angle changes to 108.5. So, for a methanol molecule, that means we are talking about an alcohol which is again a bent molecule, your bond angle is 108. When you replace both the hydrogens by methyl, and we are talking about this molecule which is a dimethyl ether, then the bond angle which is the COC bond angle, in this case it is equal to 111.7 degrees. So, in this case your COC bond angle, when you have a dimethyl ether, so this angle is 111 degrees 0.7, and you can see the change in the bond angles as you go from water to methanol to an ether. So, if you have to talk about the dipole moment or the polarity of these molecules, so you can envision that if you have these alkyl groups, okay, with oxygen being more electron withdrawing in nature, so that the net inductive effect is towards oxygen, these molecules tend to have a net dipole. So, the molecules are polar in nature. So, these ethers are polar molecules because of a net dipole moment which they possess. Okay. Some of the examples of these ethers as I was talking about. So, we discussed that you can have something like a diethyl ether, which is an all aliphatic. You can have a diphenyl ether, okay, which has both the phenyl groups, or you have a methyl phenyl ether which is called anisole. You can also have other kind of aliphatic ethers in which your alkyl groups form a cyclic ring. For example, this molecule in which you have a cyclic ether which is popularly called as THF. It is a tetrahydrofuran which is used as a solvent in organic reaction. So, you have tetrahydrofuran, likewise you can have something like a tetrahydropyran, okay, and you can have something which is two of these ether linkages which is known as a cyclic molecule known as dioxane. So, all these are examples of ethers. You can also have a 3-membered ring with one of the oxygen and 2 carbon atoms, and these are called oxyranes. You can imagine that in this case your carbon oxygen carbon, the bond angle is about 60 degrees. So, these molecules are highly strained systems, and that is why they show high reactivity and open up. Okay. So, what are some of the key physical properties of these molecules, the physical features or the physical properties of ethers? So, if you have understood that in case of ethers your oxygen is sp3 hybridized, okay, and the molecules have a net dipole moment. The properties, let us talk about the boiling point. The boiling point of these molecules is similar to that of the corresponding alkanes. Okay. So, it is similar to corresponding alkanes, the boiling point, but it is lower than the alcohols, than the corresponding alcohols. So, if you compare alcohols and ethers, then alcohols have a higher boiling point as compared to ether. So, if I just make a direct comparison between N-heptane, which is an aliphatic hydrocarbon, and its ether analog, which is again a 7-membered, a methyl N-pentyl ether, and you compare the corresponding alcohol functionality, which becomes N, a similar N-hexyl alcohol. If you compare the boiling points of these three, then your N-heptane is 98 degree, your ether is 100 degrees, and your N-hexyl alcohol is 157 degrees. Okay. So, this again you can see that it is because of the hydrogen bonding which is happening in case of the alcohols that the boiling point is high. This we discussed earlier, but in case of ethers there is no intermolecular hydrogen bonding between the ether molecules, and because of this the boiling points are similar to that of the corresponding alkanes. Okay. How do they behave in terms of their solubility features? So, when you talk about the solubility of the ether molecules, again how is their solubility in water? So, when you look at the alcohols, they were highly soluble in water because of extensive hydrogen bonding. In case of ethers, again this lone pair of electrons on oxygen, it can undergo hydrogen bonding with the water molecules, which can result in its in it getting solvated, and therefore, these can be miscible in water. So, they have miscibility in water is dependent upon the type of the ether which we are using. So, solubility in water for these molecules for ethers varies. Okay. So, it varies depending upon the type of the ether. So, for example, for a diethyl ether, the solubility in water is very low, solubility is very low, and that is why it is used as a solvent for extraction of organic compounds, right. During the workup, diethyl ether is used. It is not miscible with water, but another cyclic ether like a THF, tetrahydrofuran, this is completely water soluble. So, the solubility properties vary, and as we keep on increasing the chain length for the higher ethers, they become less soluble in water, and the lower ethers are more soluble in water. So, they have a varied solubility feature. Why are these compounds important? What are their applications? What was the first application which came out from ether? So, it was in 18th century or early 19th century when it was found that these ethers have a very important application to be used as an anesthetic. So, they were used as an anesthetic in medicine because they, and especially for the treatment of all the tooth related disorders, when they were used to cause a painless procedure during any tooth operations. So, now this is one of the halogenated ether which is called penthrene, which is a very popular anesthetic, and it is a halogenated ether which is used these days. But the earlier anesthetic which came up was the diethyl ether. So, this was a breakthrough when it was found that ethers can serve as important anesthetics in medicine. Okay. So, looking at the applications, one, it is used as an anesthetic. The second application, as I was telling you, that since it is immiscible in water, it is used as a solvent in extractions. It is used as a solvent in extractions, and it is also used for the preparation of Grignard's reagent. So, these are some of the applications of ethers in general, and when we talk about diethyl ether, diethyl ether is what is normally referred to as ether. So, when we say ether, we are talking about diethyl ether. This molecule has a boiling point of 35 degrees. It is highly flammable and water insoluble. These are some of the properties of this, which is the most widely used ethers. And another key feature is that it forms explosive peroxides with oxygen. It forms explosive peroxides with oxygen, and that is one reason why these ethers are stored in dark colored bottles, because this is a light initiated reaction. So, what is the mechanism for formation of these hydroperoxides of ether? So, this is a light induced reaction. So, for example, we talk about the diethyl ether as an example. So, this is a light mediated reaction, takes place by radical pathway. So, if you have the diethyl ether in the presence of light, it can generate this radical, which in the presence of oxygen can form this kind of a peroxy intermediate, which then abstracts a hydrogen radical from the other ether molecule, right, resulting in the formation of the hydroperoxide of ether along with the generation of this radical, which is again going back to this cycle and carrying forth all this hydroperoxide formation. So, that is why ethers are stored in dark colored bottles in order to prevent the formation of these explosive hydroperoxides. So, what is the method to determine that these hydroperoxides are getting formed in your ether bottle? You open the bottle, you do not know, but your hydroperoxide is there. So, the method of determining these hydroperoxides or peroxides in ether. So, one of the tests is the potassium iodide test. So, what is done is that you shake the ether, you take some amount of ether, let us say 10 ml, and you shake it with the solution of potassium iodide. Okay. You shake it with the solution of potassium iodide, let us say for 10 ml it is 1 ml, 10% weight by volume of potassium iodide and a few drops of HCl mixed with it. So, you shake it, and when you shake it you will find that the iodide gets oxidized to iodine, right. So, you get iodine from iodide, and this changes the color of the solution to yellow. So, the solution turns yellow in color, and this you can further confirm if you add few drops of starch to this, and you will get a black violet color. So, this tells that the ether solution is containing some amounts of hydroperoxide. Another way of determining this could be by treating it with ferrous ammonium sulphate and potassium thiocyanate solution. So, you take the ether solution and shake it with a mixture of ferrous ammonium sulphate and potassium thiocyanate aqueous solution. So, when you do so, the peroxide, what it does is, the peroxide reacts with the ferrous ions and oxidizes them to ferric. Okay. So, this is the oxidation reaction, ferrous to ferric, and then these react with the thiocyanate ions which are there from potassium thiocyanate, and you get this kind of the ferrous thiocyanate complex, the ferric thiocyanate complex, which is red in color. So, this is another indication that the peroxides are present in your solution. Now, how to remove the peroxide impurity? So, the removal of the peroxides from the ethers is important in order to avoid any accidents when you are using ether as a solvent. So, in order to do that, so once you have seen that it contains impurities, one way is that the ether can be washed or shaken with, you wash it with ferrous ions. Okay, you wash ether with ferrous ion solution. So, the ferrous ion solution could be solution of ferrous sulphate, and what it does is it reduces peroxide. So, this is one of the ways of removing the peroxide impurities. Or the second thing, you can distill the ether from concentrated H2SO4, which results in oxidation of peroxide. So, it oxidizes peroxide. So, these are the two ways in which we can convert the peroxides into the non-harmful forms and clean up our ethers. Okay. So, this was about the general properties, the solubilities, the boiling point and other characteristic features of ethers. So, now we talk about the synthesis, the methods of preparation of ethers. Okay. So, we next go to the synthesis or the preparation of ethers. So, the most popular synthetic protocol for making ethers is a name reaction which is called Williamson synthesis. So, Williamson synthesis is a method which is used to make unsymmetrical as well as symmetrical ethers. So, you are talking about two different alkyl groups or two identical alkyl groups. So, this has the capacity to make both the unsymmetrical as well as symmetrical ethers with the help of a substitution reaction, which is the SN2 reaction in this case. So, what we do in Williamson synthesis is you take the alkyl halide, which is primarily a 1 degree alkyl halide, and treat it with sodium alkoxide. Okay. So, this is the sodium salt of an alcohol which is called sodium alkoxide. So, when you react the alkyl halide with sodium alkoxide, you get the corresponding ether along with formation of sodium halide. So, in this case, as I told you, the limitation is that this has to be a 1 degree alkyl halide. Why so? Because the reaction which is involved here is a SN2 type of reaction. So, it is a SN2 substitution reaction. For example, you take methyl bromide and you treat it with sodium tertiary butoxide, and in this case what you get is a methyl tertiary butyl ether. So, there is a nucleophilic substitution of the alkoxide. The alkoxide replaces the halide ion. So, nucleophilic substitution of the halide ion by the alkoxide. So, this is your leaving group. So, in the same manner, if you generalize it, that your alkoxide ion and this is your 1 degree alkyl halide, the nucleophile attacks the alkyl with the simultaneous loss of the leaving group, and you get the ether, and this is your leaving group. So, in this case, if we want to make unsymmetrical ethers, what are our limitations? So, we have, suppose we want to make this molecule. So, we have two choices, we have two routes through which we can proceed about making these molecules. One could be that we start with ethyl bromide and treat it with the sodium salt of tertiary butanol. The second option could be that we start with the other halide, tertiary butyl chloride, and treat it with the sodium salt of ethanol, in this case sodium ethoxide. So, the question is which of the two is the correct approach towards making this molecule. Okay. So, as I was explaining that in this case the approach, the reaction which is going to give you the product will be this reaction and not this reaction, simply for the reason that we have to understand that these alkoxides which we are using, they not only act as nucleophiles. Okay. So, they behave as nucleophiles, but they also behave as strong bases which can result in a competing elimination reaction. So, there is always a competing elimination reaction which will happen if your alkyl halide is not a 1 degree. So, this, if it is a 1 degree alkoxide, elimination is very minimal or it is not there, but if you have 2 degree and 3 degree alkyl halides, in this case the elimination product will also be seen along with the substitution product, which is the ether. Okay. So, that is why preferably in Williamson synthesis, when we are doing a SN2 substitution, it is the 1 degree alkyl halides with which the procedure is most successful. All right. The second method for synthesizing these ethers is an analogous method what we discussed for alcohols, which was mercuration, oxymercuration, demercuration. In this case it is called alkoxymercuration demercuration. So, this is similar to what we studied earlier, nothing changed for alcohols. The only thing is that instead of the water molecule, in this case it will be the alcohol molecule which will add up onto the alkene. So, it is similar to the oxymercuration demercuration in alcohols. The starting product material is the same, you start with an alkene and you treat it with the mercury salt, which is mercuric trifluoro acetate, and this is happening in presence of alcohol as one of the reagents. So, what you get is this intermediate after alkoxymercuration, which when subjected to reduction with sodium borohydride gives you the corresponding alcohol after reduction of this mercury group. So, the addition, as was seen with case of water for making alcohols, it follows Markovnikov's addition, which means that again if you have different substituents placed on the olefin, that the hydrogen is going to add to the carbon which is less substituted. Okay. The Williamson synthesis can also be applied to alkyl aryl ethers. Okay. So, I take the alkyl aryl ethers separately just to say, but the method is the same, the Williamson ether synthesis. So, you take the phenol right, as instead of the alkoxide you can take the sodium phenoxide. So, you take this or sodium phenoxide in this particular case and you treat it with alkyl halide. So, again you can have an alkaline solution. So, you can have aqueous NaOH. If you are using a phenol, you use aqueous NaOH, right. You maintain an alkaline solution and you get the corresponding alkyl aryl ether. So, these are the general conditions. So, as a representative example, if you start with any halide, let us say a benzyl bromide, and treat it with not a preformed sodium phenoxide, but a phenol in aqueous NaOH, you get the corresponding alkyl aryl ether, right. It could be this, or another reagent which you can use instead of the alkyl halide with phenols, it can also be a methyl sulfate, which in the presence of aqueous NaOH again can give you this particular ether, which is popularly known as anisole. So, you get anisole along with the formation of this salt. It is a cheaper reagent, it is cheaper reagent compared to the corresponding alkylating agent which you would have used in this case as an alkyl iodide or something. So, it is cheaper reagent than your corresponding methyl halides. Okay, so, in this case again just look at the reagent combination. Suppose you want to make this particular ether. So, you have a propyl group on one side and a phenyl on the other side, a propyl phenyl ether. So, how do you go about it? Again you have two choices, two routes to think about. So, one could be that you start with propyl bromide and treat it with sodium phenoxide, and the other route could be that you start with sodium propoxide and treat it with aryl bromide. Okay. So, again the question is that whether you want to use the sodium phenoxide or you want to use the aryl bromide. So, this particular path does not happen. In fact, the reaction goes through this pathway because one can give a rationale. It is because of the low reactivity of these aryl bromides towards the nucleophilic substitution. So, the aryl bromides are not good substrates towards nucleophilic substitution. Across this is difficult, and that is why we will not use this particular combination in order to carry out the synthesis of these kinds of ethers. We move on to the other class of ethers. So far we have talked about the cyclic, the non-cyclic ethers like your dialkyl ethers or the aryl alkyl ethers. Let us see how do cyclic ethers behave in terms of their synthesis, or what are the general methods for preparation of cyclic ethers, which are also called epoxides. So, again depending upon the ring size of the cyclic ether, if you have a 3-membered ring with one of the atoms oxygen, this is called oxyrane. If you have a 4-membered with one of the atoms oxygen, it is called oxytane. So, oxy is telling that there is an oxygen, and the rest of this is telling about the chain length of the cyclic ether. If it is a 5-membered, which we just saw a few minutes ago, we called it tetrahydrofuran, and this is called oxolane as a general nomenclature, the 5-membered. And if it is a 6-membered, then it is called a tetrahydropyran, or this is an oxane ring. And if you have a 6-membered with 2 of these ethers, it is a bifunctional, you call it a 1,4 dioxane. So, these are some of the popular cyclic ethers which we know of. Okay. So, one of the methods for preparing these cyclic ethers is by the air oxidation of ethylene. So, when you want to prepare a 3-membered oxyrane type of ring, the simplest way is you carry out the aerial oxidation of ethylene or ethene in the presence of silver oxide as the catalyst at 300 degrees centigrade, when you get the corresponding ethylene oxide as your product. Okay. Another method for making the larger cyclic ethers would be by dehydration of diols. So, you start with a butane diol, you can start with a butane diol, a 1,4-butane diol, and you carry out dehydration with concentrated sulfuric acid, and you get the 5-membered cyclic ether, which is your THF, along with elimination of water molecule. Likewise, you can choose a 1,5-pentane diol, so this is 5, okay, 1, 2, 3, 4, 5, and again you with this 1,5-pentane diol, if you heat it with concentrated H2SO4, high temperature 140 degrees centigrade, you get the 6-membered tetrahydropyran along with formation of water molecule. So, this is in fact a general method. The dehydration of alcohols is a industrial scale method for preparation of ethers, which can also work in fact for alicyclic ether. So, even if you have regular acyclic alcohol, you can treat it with concentrated H2SO4, just simply you have to heat it. When you get the corresponding ether, the only difficulty with this reaction is that this is not optimized same for all types of alcohol. So, for example, the competing reaction always exists in this case. So, if you have ethanol and you do this dehydration at 180 degrees centigrade, you end up getting ethene, you get the elimination product, right. But if you do the same reaction with ethanol at 140 degrees centigrade, it is then that you get the diethyl ether. So, there is a nucleophilic substitution versus elimination which are competing, right. So, the nucleophilic substitution is happening when the alcohol is in excess and at a lower temperature, right. In this case, the first step is the protonation of the alcohol, followed by the attack of the second alcohol molecule to form this ether. But in the other case, there is a competing elimination reaction if the temperature is higher. So, the dehydration of alcohols is also applicable for getting ethers, the acyclic ethers, and this normally will happen, it is going to end up giving you symmetrical ethers. So, this is a good method only for symmetrical ethers, while Williamson synthesis was able to give you unsymmetrical ethers as well. Okay. And normally again it would be best when you have 1 degree alcohols here, because with again 2 degree and 3 degree you are going to get amounts of elimination product as well, which is kind of a side reaction for us and not needed. Okay. Another method for making these cyclic ethers is by the vicinal, is from these vicinal halohydrins, which change to epoxide. So, your vicinal halohydrins, which you, if you recollect, we did it earlier when we were talking about the alcohols, that you form this kind of a hypohalous acid can form, and it undergoes an addition reaction on the olefin double bond, and you get this kind of a halohydrin, which under alkaline conditions, okay, in the presence of the base, can result in the formation of epoxides. This we did earlier also. This is one of the method for preparation of these cyclic ethers, which is the vicinal halohydrin to epoxide. Okay, so this was all about the different methods of preparation of ethers. right. So, we have seen that when we have to prepare cyclic ethers, acyclic ethers, by and large there are 2-3 general strategies, and depending upon the nature of the ether which we want to prepare, we choose the right combination of the two substrates, one which is the alkoxide if you are doing Williamson synthesis, and second which is the alkyl halide, which is generally a 1 degree alkyl halide if we want to prevent the elimination from taking place. That is a competing reaction and which lowers the yield in most of the cases. So, that has to be taken care of. Okay, so, what are the reactivities and the chemical reactions of ethers? So, ethers have a very few set of reactions normally what they can undergo, because the carbon oxygen bond is quite strong. So, the general categories, the one of the important class of reactions is the ether cleavage reactions. So, we have ether cleavage reactions in which you have your ether, okay, which is your COC bond, and you have a nucleophile which comes and attacks on this carbon. Okay. So, you are talking about the cleavage of the CO bond, how can it happen? So, if the nucleophile comes and attacks from the back side and you are able to force the reaction to give you this substitution product, then what is the probability of this reaction to happen? So, by and large we see that if directly a strong nucleophile comes and attacks ethers, it is not able to carry out the cleavage of the CO bond. Okay. So, the reason is that your CO bond is quite strong, right. And the second thing is that your leaving group, which is alkoxide in this case, it is a poor leaving group. So, your alkoxide ion is a poor leaving group, and because of these two reasons, a direct cleavage of the CO bond by attack of a nucleophile is very less probable. Okay. So, just except your oxyranes, right, the ethers are not directly cleaved by strong nucleophiles. So, the only exception to this are oxyranes, where directly the CO bond can be cleaved because they are highly reactive species. As I told you, it is a strained molecule. The cyclic ether, the oxyrane is the only one which can be cleaved directly by attack of a nucleophile, but not the aliphatic ether. So, for the cleavage, what are our options? So, in order to carry out the cleavage of the CO bond, we have to activate that ether linkage. Okay. So, the ether linkage has to be activated. So, this is the condition that has to be satisfied in order to break the ether bonds, that it has to be activated. So, one of the ways would be that you make use of this cleavage by using a stoichiometric amount of acid. So, you use stoichiometric amount of an acid which activates the oxygen. So, what it does is that you have your ether, and you add an acid, right. The first step is the protonation of the ether. The proton, you should, okay, it goes and adds on to your oxygen site, and this gets protonated. Now, after this, now the next step could be the attack of the nucleophile. So, when you have activated your ether, now the nucleophile can come and attack either through SN1 pathway or through SN2 pathway. So, now the nucleophile can come and attack. So, which is the pathway it is going to choose? It again depends upon the nature of these alkyl groups on the ether. So, if you have 1 degree and 2 degree ether carbons, okay. So, if your ether is comprising of the alkyl groups which are 1 degree and 2 degrees, and you have a strong nucleophile. So, I am talking about the conditions, and you have a strong nucleophile. Let us say we are working with an iodide, then it is the SN2 path which will operate. So, SN2 operates, and what will happen that your nucleophile is going to attack on which of the 2 carbons of the alkyl group? The attack will be on the less hindered carbon, as would be the typical characteristic of an SN2 reaction, that the attack is on the less hindered carbon and you get a less substituted alkyl iodide and a more substituted alcohol. So, this is what is going to happen primarily, that these are the major products if your ether is carrying the alkyl groups which are 1 degree and 2 degree. So, just to represent it, you have your COC linkage, one side your alkyl group of the ether is a 2 degree alkyl group, one side it is a 1 degree alkyl group. The first step is the protonation, which is activating your ether, right. So, you have your protonated oxygen. So, now you have the choice of a 1 degree and a 2 degree alkyl group. So, your iodide, which is the nucleophile, is going to come and attack on the carbon which is less hindered. Okay. So, this goes and attacks here, and you end up with the products which are the less substituted alkyl iodide. Okay. So, your alkyl iodide is less substituted and your alcohol is the one which is more substituted. It contains that alkyl part which was more substituted. Okay. So, this is one of the conditions. The second condition could be that if one of the ether carbons, is 3 degree, okay, if it is 3 degree, now it can yield a stable carbocation. Okay. It is capable of yielding a stable carbocation, right. And now, once you have a carbocation, from there on both your SN1 and E1 can operate. So, what you will get from here, if it is a 3 degree alkyl group on the ether, you will get the alkyl halide which is more substituted, you get a more substituted alkyl halide and you get the less substituted alcohol. So, it reverses what we just saw a minute ago when it was a 1 degree or a 2 degree. So, if you have a 3 degree alkyl halide at one place in the ether, right. So, the first step, which is the protonation, has happened already. So, now it can stabilize to a stable 3 degree carbocation. So, that after that, when the nucleophile attacks, what you get is this alcohol which is less substituted, and you get on this stable carbocation the attack of the nucleophile which gives you the alkyl halide. Okay. So, again there are two possibilities here. So, you can get the alkyl halide which is the more substituted alkyl halide, or it can undergo loss of a proton, that is elimination reaction, which is always competing with the 3 degree carbocations, and you can get the corresponding elimination product. So, you can get both the elimination product as well as the substitution product by the SN1 pathway. Okay. So, this is the general reactivity of the different alkyl groups in case of ethers. If you have comparable, okay, so if we have the R's which are comparable, okay, so if we have comparably substituted carbons, then you end up with a mixture of products. Then it is very difficult to control the product distribution. So, if R and R dash are similar, like 2 degrees, 3 degrees, they are similar in their stability orders, and if you treat it with Hi and you want to bring about the cleavage of the ether, the CO bond, then in this case you will end up with a mixture of two products. One will be this halide and this alcohol, and the other would be this halide and this alcohol. And if one of your R's is an aryl group, okay, what will happen if it is an aryl group? And if it is an aryl group, you can imagine that both SN1 and SN2, they cannot occur on the aromatic carbon. SN2 cannot occur on aromatic carbon, and even SN1 cannot occur on aromatic carbon. You can see here that if it is this molecule phenetol ethyl phenyl ether and you try to cleave it with Hi. So, your first step is the protonation, which gives you this protonated ether, and now when your iodide comes, okay, so when I minus comes, it cannot attack here, right. This is not susceptible to it is not stable carbocation, your phenyl, and SN2 cannot occur from the rear side. So, the only option which you are left with is that in this case you only end up with these two products, which is a phenol and the alkyl halide. So, this is about the cleavage of the acyclic ethers, which is the acid catalyzed cleavage. Right. So, now we again try to see what happens in case of oxyranes. So, oxyranes also undergo acid catalyzed cleavage. So, the first in a similar manner, which is the acid promoted cleavage for oxyranes. So, we have this oxyrane. Again, the first step is your protonation, right, and what you get is, so it is an unsymmetrical oxyrane, as you can see both the carbons are differently substituted. So, you get this protonated oxyrane. Okay. So, now you have two carbons. So, your C1 and C2. Okay. Now, the question is, where is the nucleophile going to come and attack? So, your nucleophile, when it has to make a choice between C1 and C2. So, if this positive charge resides on C1, it will be stabilized much more. So, this C1 carbocation will be stabilizing much more because of the two alkyl groups, and therefore, this positive charge, since it is more stabilized on C1, the nucleophile prefers to attack C1, right, and therefore, the product which you get on ring opening of this epoxide is with the C1 substituted with the nucleophile and the C2 bearing the hydroxyl group. Okay. So, this is one of the aspects of the acid promoted cleavage in case of oxyranes, that where is the nucleophile going to open up the ring. The reacting C1 which we just saw, it undergoes inversion of configuration. It undergoes inversion of configuration, which indicates that the reaction might be through SN2 mechanism, that it might be going through an SN2 pathway. Okay. So, the mechanism probably for this, what is happening here is that you have your oxyrane, so you protonated it, that is your first step, the protonation of your oxyrane, right. Now, when the nucleophile comes and attacks, it attacks the more substituted carbon, okay, because of the significant carbocationic characteristic of the carbon in this intermediate, and after the reaction when it opens up, then what you get is a ring. The ring open product has an inversion at this carbon center. Okay. So, your nucleophile, your R dash and your R, this is OH, this is R and this is H. So, this carbon, okay, it shows an inversion, and this carbon shows the retention of configuration as a result of the ring opening. So, this is similar to something, you know, a cyclic intermediate, the bromonium ion intermediate. If you recollect, it is similar to the bromonium ion intermediate, in which also there is a backside attack of the nucleophile. Okay. So, this is cyclic intermediate, and the attack of the nucleophile is from rear, because of which there is an inversion of configuration at this C1. Okay. In case, so one of the cases could be that if both R and R dash are highly substituted. Okay. So, if both R and R dash are 3 degree, then you will have in that case a carbocation So, if you have R dash and R, okay, in this particular case, and you get this carbocation. Okay. Now, in this case, if the charge is highly stabilized on this carbon, then it can even open up. Okay. So, instead of staying as a bridged cyclic intermediate, it can open up to give you a open chain carbocation, and if you get that carbocation species, then you end up getting a racemic product mixture. So, if these carbocation, if these alkyl groups tend to stabilize this carbocation extremely well, then this is going to open up in the first step, right, and before the nucleophile attacks, and in that case you are going to end up with a racemic mixture of the products. Okay. So, this is the possibility that what will happen, that it opens up and it gives you a discrete carbocation before the nucleophile attacks in your SN1 pathway, okay, and then you end up with the mixture of two products, one with the retention of configuration okay. So, we just put this, and one with the inversion of configuration where the nucleophile attacks from the same site. Okay. So, you get the mixture of these two products if the reaction during the reaction this intermediate opens up. Okay. The second, which I told you, which is not possible for the acyclic ethers, is the nucleophile promoted cleavage, which can only happen for oxirane. So, you have a nucleophile promoted cleavage, which is a pure SN2 pathway. Okay. This is a pure SN2 nucleophile promoted cleavage. So, what is happening in this case is that you have your oxirane, right, and a strong nucleophile can come and attack the less hindered carbon, okay, and this gives you this intermediate alkoxide, which upon the acidic workup will give you your final product through the ring opening of the epoxide, which is the alcohol. So, this happens only for these systems, and if you look at it, observe it carefully, you can see that on this side there is the retention of configuration, while on this side, since the nucleophile is attacking from the back side, this carbon, the configuration is inverted. And if your nucleophile happens to be a Grignard's reagent, then it can result in the formation of a new carbon-carbon bond with the help of the nucleophile assisted ring cleavage of oxygenanes. Okay, so the last example I am going to talk about the ethers is a very popular rearrangement reaction, which is known as the Claisen rearrangement. So, this is one of an important interesting rearrangement reactions of ethers, and which ethers? This is shown by allyl aryl ethers when they convert to ortho-allyl phenols when subjected to heat. So, this popularly is known as Claisen rearrangement. So, if you have this allyl aryl ether and you heat it at about 200 degrees, you get a rearranged product, which is this phenol on this side, and the entire allyl group comes at the ortho position, and you get these ortho-allyl substituted phenols, right. So, the question could be that if your ortho position is blocked, then what happens? So, if your ortho position is blocked with 2 alkyl groups, let us say 2 methyl groups, and you again subjected to the Claisen rearrangement, then the allyl group travels to the para position, it moves to the para position to give you this para substituted phenol. So, this is a very interesting reaction because it allows you to get these allyl substituted phenols. So, probably what is happening here is that this kind of a cyclic reaction to give you this intermediate first. Okay. So, you have a CH2, CH double bond CH2, and then this moves back to give you the phenol. So, we are getting these products as a result of Claisen rearrangement, a very useful reaction. Okay, so, I am going to stop here. This is all about ethers, their preparation, their reactivity, their cleavage reactions, their physical properties. So, we will stop with this, and that brings us to an end of the chapter, which is the alcohols, phenols and ethers. Thank you.